Watch the coastal megacities flicker to life after dark. The sheer density of this nightly grid requires an overwhelming, continuous draw of electricity. Keeping these cities online puts an immense strain on the national grid. Heavy manufacturing demands, rapidly expanding high-speed rail networks, and unchecked urban sprawl are consuming power at a rate the current infrastructure struggles to sustain. For decades, coal was the primary engine for this growth, but choking industrial smog and severe environmental degradation forced a hard pivot. The government had to find a way to maintain their economic momentum without suffocating their own population. To clear the air and keep the factories running, they need a massive influx of clean energy. The scale of this domestic demand is so vast, it requires looking to the extremes of geography for a solution. Thousands of miles west, far from the neon skylines, lies the Tibetan Plateau. In these elevations, glacial meltwater gathers to form the origin point for some of the continent's most powerful river systems. Measured against the Hoover Dam and Burj Khalifa, the vertical scale of this new installation becomes clear. Engineers plan to wedge a massive wall of concrete directly into this topography, bottlenecking the valley entirely to retain billions of cubic meters of glacial runoff. This project represents a macro-scale terraforming of the Earth's surface, designed to bridge the gap between rural geography and urban energy demand. As gravity forces the trapped water through narrow penstocks, the kinetic energy of the river spins massive turbines, generating hydroelectricity at the source. This map illustrates the intended grid acting as a high-altitude battery. Tens of gigawatts of electricity flow eastward across transmission lines into industrial centers. But bottling a river restricts the natural flow heading south, managed by a single gatekeeper before crossing international borders. Securing energy independence at the river's source results in direct physical control over the water supply for the nations living below. As the river leaves Chinese territory and enters India, Bangladesh, and Myanmar, it becomes a critical lifeline for millions. Entire ecosystems rely on its predictable, seasonal cycles. Crops, fisheries, and local economies depend on the steady pulse of these waters. For downstream governments, the immediate threat is artificial drought. If upstream operators restrict the gates during the dry season, water levels can drop, resulting in stranded boats and empty channels. The opposing risk involves sudden, uncoordinated releases of water during heavy rains. If the dam's operators clear their reservoirs without warning, it can trigger flash floods that destroy downstream harvests. The project transforms a shared natural resource into a geopolitical lever, placing the regional water supply under centralized control. Beyond the political tensions, the project faces a physical reality. The Himalayas contain some of the most active seismic fault lines on the planet. This cross-section shows the underlying danger. You are placing an enormous, concentrated column of water, weighing billions of tons, directly over converging tectonic plates. If a severe earthquake were to rupture the concrete, the sudden failure of the reservoir would unleash a wall of water down the valley. Planners have conducted safety tests to ensure the structure can withstand tremors. Yet human engineering is rigid, while the Earth's geology is unpredictable. Human engineering is attempting to stabilize a site prone to tectonic shifts, escalating a water dispute into a significant physical risk. The presence of this dam creates a new regional reality, where the river's path is defined more by policy than by nature. Every country to the south must now factor a foreign engineering schedule into their own agricultural and security planning. The dam offers a massive leap toward decarbonization, promising tens of gigawatts of electricity exactly where it is needed most. But the collateral risks to the region are significant. Time will dictate if this project stands as a clean energy triumph or the catalyst for a sprawling environmental crisis. If you trace this river system back to its source, you end up high in the mountains of China. From there, it cuts a path straight down through India, Bangladesh, and Myanmar. Hundreds of millions of people rely on this exact network of water. It irrigates their crops, sustains local economies, and serves as a continuous lifeline spanning multiple borders. Right near the source, engineers have embedded this massive concrete structure into a steep mountain canyon. By placing a megadam here, a single country has installed a physical plug in the region's main artery. When you control the headwaters, you dictate what happens downstream. Holding the physical switch to the river flow gives the upstream nation enormous leverage over every neighbor waiting for that water. The rest of the world is watching this development closely. Tracking how this dam operates is a geographic necessity for maintaining stability across the continent. Building anything at this altitude requires navigating a barren, rocky valley isolated from major supply lines. The site is battered by sudden, intense rainfall, swelling the mountain rapids. The water accelerates through the canyon, generating massive kinetic energy, hammering the riverbanks. Standard concrete walls are designed to hold weight, but they struggle against the combined forces of violent currents, extreme weather, and seismic shifts. Under these conditions, traditional static engineering simply cracks. Survival in this environment requires an active, technologically aware defense system that responds to the river in real time. Engineers embedded thousands of high-tech monitoring sensors directly into the concrete body of the dam itself. This diagram shows how these nodes are distributed through a cross-section of the wall, tracking deep water pressure and microvibrations. All telemetry feeds into centralized algorithms. Modeling these stress patterns helps engineers predict structural fatigue long before a physical crack forms. The concrete holds the water back, but this invisible, predictive digital nervous system is what actually keeps the entire facility from collapsing under the extreme environment. Once the water passes through the spillways, it returns to a wild, untamed state as it rushes violently over rocks and fallen timber. But holding back millions of gallons in an upstream reservoir changes the water. The timing, the volume, and even the temperature of the flow are permanently altered from their historic baseline. The dam traps the rich silt that usually flows downstream. Wide, dense tropical forests like this rely heavily on that sediment, acting as a natural fertilizer during the flood season. Without that sediment, and with sudden shifts in water temperature, seasonal fish migrations are thrown out of sync, severely threatening local biodiversity. Securing clean energy at the river's source creates a cascading, long-term ecological debt for every region below. The ecological costs of the dam ripple directly into the lives of millions of people living along the downstream borders. If engineers suddenly release water to relieve pressure at the dam, towns in India and Bangladesh can experience catastrophic, unannounced flooding, forcing residents to wade through deep water just to reach basic resources. This 3D map illustrates the only viable defense against these disasters, a transparent system where hydrological data packets are transmitted in real time from the dam site directly to warning centers across the border. But that system requires cooperation between rival nations. Millions of downstream citizens have to trust an upstream competitor to provide life-saving environmental warnings. In this region, the real-time data describing the river's flow is as valuable as the water itself, used by the upstream nation as a primary tool for regional influence. As the turbines spin, the question remains, will this massive structure stand as a lasting monument to human engineering and clean energy, or will its complex downstream impacts trigger a permanent global dispute?
Welcome to this explainer. Okay, today we are looking at China's mega dam, exploring power, progress, and environmental equilibrium. And wow, we're talking about something that truly redefines human engineering. Just picture this, on an IMAX scale, a colossal concrete titan nestled within a vast valley, stretching all the way across a roaring river. This isn't just a building, it's a mega dam. It's this monumental intersection of immense power, rapid national progress, and the super fragile environmental equilibrium of our planet. To give you an immediate sense of the absolute scale we're dealing with here, this structure holds back so much water that the sheer, concentrated mass of that reservoir actually slightly alters the rotation of the Earth. I know, no way, right? It's a literally mind-boggling reality. So, we're going to unpack the breathtaking magnitude of these megastructures, breaking down exactly how they work, why they're built, and the immense complexities they bring to the world stage.
Okay, let's dive into this. Millions of liters of water. Not a day, not an hour, but every single second. Imagine the ultra-realistic physical reality of that flow. Just picture the roaring, chaotic, relentless power of a massive river being corralled and forced through these highly engineered corridors. The immense pressure builds up behind millions of tons of concrete, and then, boom, the water is funneled down through massive pipes, they're called penstocks, at terrifying, bone-rattling speeds. As the water crashes through the bottom of the dam, it slams right into colossal turbine blades. That sheer physical, absolutely unstoppable force is instantly transformed into the electrical lifeblood that can literally light up entire cities in a flash. It's an epic, continuous cycle of kinetic energy. And understanding this relentless, roaring physical journey, well, that's the absolute first step in grasping why nations invest billions into these monumental projects.
So what does this all mean? At its core, this entire operation boils down to one ancient concept, just scaled up to a modern, almost unimaginable extreme: hydropower. The mechanics here are, well, they're as old as wooden water wheels turning millstones, but modernized to generate staggering power. By harnessing that rapid flow of water through those heavy-duty turbines we just talked about, the kinetic energy spins massive electromagnets inside copper wire coils. That spinning magnetic field induces a continuous, heavy stream of electricity. And the absolute most critical part of this entire process, it's incredibly clean energy. I mean, think about it. When you have a megastructure capable of channeling millions of liters of water to generate thousands of megawatts without burning a single ounce of fuel in the immediate process, you suddenly have a primary engine for renewable power that can sustain millions of people.
Now imagine taking a drone fly-through shot across the landscape. Historically, powering massive growing nations meant a really heavy reliance on coal-fired power plants. And that reliance, unfortunately, brings dense smog and skyrocketing carbon emissions that just blanket entire regions. But transitioning the heavy lifting of electricity generation to these megadams, that allows a country to drastically rethink its entire grid. By relying on hydropower, those smoky, older power plants can slowly be phased out. Get this, a single megadam can offset tens of millions of tons of carbon emissions every single year. Tens of millions! It's a profound shift in how a nation breathes and operates, literally replacing fossil fuel combustion with the perpetual motion of the water cycle.
But here's the catch. You can't run a modern nation on just one power source. A river can experience severe seasonal droughts, just like the wind can stop blowing or the sun can set. The reality of powering a modern country requires a carefully balanced mix of various energy sources to ensure absolute stability. If the water levels drop too low in the reservoir, the turbine spins slower and the power output drops. That means national energy policies have to rely on a complex, multi-source approach. Hydropower from a megadam is a massive, incredibly clean piece of the puzzle, for sure. And it acts as an amazing baseline. But it's still just one piece of a much larger, intricate national energy strategy that has to account for literally every single contingency.
And here is exactly why that energy strategy needs to be so completely bulletproof. The demands of a booming economy are fast, relentless, and growing by the millisecond. We're talking about brightly lit metropolises that never sleep. We're talking about high-speed rail networks crisscrossing the country at hundreds of miles per hour and enormous industrial factories pumping out global goods around the clock. And, crucially, this is a big one, we have massive power-hungry data centers, especially right now with the staggering energy demands of artificial intelligence. I mean, these facilities are processing the digital backbone of the modern world, and they draw an unbelievable amount of power. This rapid economic boom requires an absolutely staggering, constant supply of electricity. This immense, unending demand is the primary driver forcing expanding economies to invest in these colossal megaprojects. Because at the end of the day, they simply cannot afford for the lights to go out.
Now, let's slow the tempo down for a moment. Let's step away from the glittering high-tech cities and move down the river to the human level. For the farmers, the riverside villages, and the agricultural communities located hundreds of miles below the dam, their entire livelihood is completely dictated by the river. And it's not just about having water. It's about a delicate, critical dependence on the precise timing and the exact volume of that water. A megadam inherently alters the natural, historical rhythm of the river. Think about it. If operators suddenly release a massive surge of water to meet peak energy demands in a faraway city, well, it can unexpectedly flood a farmer's crop downstream. Conversely, holding water back to fill the reservoir for future use can cause a localized drought just when those crops need water the most.
And it brilliantly illustrates the ultimate paradox of the megadam. On one side, you have the undeniable need for energy, booming industry, and the modern infrastructure required to lift millions of people into economic prosperity. It is an unstoppable force of momentum. But on the other side, you have the vital importance of the natural environment, the ancient forests, and the highly complex, fragile ecosystem of river wildlife that has evolved over millions of years. Both sides hold immense, undeniable weight. It's this constant physical clash between the unstoppable force of human economic progress and the critical, existential need for ecological preservation.
Managing this clash? Well, it requires an incredibly difficult tightrope walk.
The operators of these megastructures aren't just, flipping switches and opening valves. Actually, they rely on advanced, complex algorithms and highly sophisticated meteorological forecasting to predict rainfall and manage the reservoir levels day by day. They have to generate enough power to keep those high-speed trains running and the AI data centers cooled, while simultaneously ensuring that the downstream farmers get the exact water flow they need, precisely when they need it, all while attempting to protect the river's natural flora and fauna. It is quite literally a minute-by-minute, scientifically rigorous balancing act between the insatiable demands of human economics and the ancient necessary rhythms of nature.
So, as we wrap up today's explainer, we have to look toward the future. How will this colossal structure withstand extreme natural events? With changing global climates, what happens when this mega dam faces unprecedented, record-breaking rainfall that completely exceeds historical data? What happens to those millions of liters of pent-up water if a massive, valley-shattering earthquake strikes the bedrock beneath it? The engineering is hailed as flawless, but in a world of increasingly unpredictable and violent weather, we really have to ask, is it flawless enough? Because in the face of nature's most extreme fury, the safety systems of these colossal structures are the very last thing standing between progress and potential catastrophe. We'll see you in the next explainer.
When we picture a mega dam, we typically see a silent wall of concrete, passively holding back the weight of a river. Deep inside the structure, a centralized control room processes an endless flow of telemetry, running 24 hours a day to manage the reservoir. Thousands of embedded sensors continuously track the rising water pressure, shifting temperature gradients, and internal structural stress in real time. This data allows engineers to identify microscopic shifts in the concrete, fractions of a millimeter, long before they manifest as visible cracks. The stakes of this monitoring are absolute. If a critical weak point goes undetected, the resulting structural breach would release a catastrophic, lethal wall of water onto the millions of people living in the vulnerable valleys downstream. The megadam functions as a reactive digital organism, using this continuous awareness to negotiate the immense forces pushing against it. Zooming out from that digital telemetry reveals the immense physical scale required to translate data into physical defense. The most immediate threat to this barrier is the arrival of extreme weather systems that dump massive volumes of rain across the watershed, causing reservoir levels to spike in hours. To counter this influx, the structure utilizes a series of massive steel spillway gates. By opening these gates, operators execute a highly calculated release, venting just enough water to relieve the weight against the primary wall while matching the river's downstream capacity. Surviving the deluge requires balancing the reservoir's pressure against the physical limits of the concrete. While weather attacks from above, the dam's location in an active seismic zone means it also faces tectonic threats from below. The concrete's geometry is designed to absorb kinetic energy. As tremors travel from the bedrock, the wall's massive sloping base disperses the shockwaves. Engineers run simulated earthquakes against specific internal stress points, confirming the structure withstands violent vibrations without shattering. Controlling a river requires a structure rigid enough to hold a flood, yet resilient enough to endure the movement of the earth. Engineering manages the physical threats, but the project's ultimate survival depends on international diplomacy. This river originates in China, but its waters flow continuously across borders into India and Bangladesh, moving independently of political boundaries. Because of this shared geography, downstream safety hinges on the upstream nation sharing accurate hydrological data about flow rates and releases. Joint scientific studies and transparent communication provide the common ground necessary to ease the friction inherent to shared waterways. Thousands of tons of concrete provide no protection if human cooperation breaks down. In this context, diplomacy is the final structural support. Zooming out further reveals the difficult trade-off of the mega dam era, the tension between economic modernization and environmental loss. These structures generate staggering amounts of electricity, providing the power necessary to modernize nations and sustain vast, growing urban centers. Capturing that energy requires permanently altering a river's natural flow. It floods ecosystems, disrupts migratory wildlife, and displaces communities from their generational homes. This tension is the defining challenge of modern development, forcing a choice between human expansion and ecological preservation. When viewed from orbit, the true scale of this intervention becomes clear. Megadams are the ultimate test of human responsibility. They force us to decide if controlling nature at this magnitude is a sustainable path forward. Tell us in the comments, is this scale of engineering necessary for our future, or should we be looking for a different way?